Okay, let's talk about something you see every day. Ever wondered why a rusty old iron gate looks so different from a shiny gold ring that never seems to change? Well, the answer is all about something called metal reactivity. And trust me, understanding this is going to be your secret weapon for nailing those chemistry questions on your exams.
So, over the next few minutes, we're going to cover everything you need to know. First, we'll break down what reactivity even means. Then, I'll introduce you to your new best friend, the reactivity series. After that, we'll get into the rules of displacement, and finally, we'll put it all together and tackle a real exam-style question. All right, let's dive right in. First things first, what are we actually talking about when we say a metal is reactive? Let's go right back to that first question. You've got an iron fence that rusts and falls apart, but a gold ring that can last for thousands of years looking perfect. It's not magic, you know. It all comes down to how reactive each of those metals is. So, what is it? Put simply, reactivity is just a way to measure how eager a metal is to get involved in a chemical reaction. Think of it like this. Some metals are super outgoing. They want to react with everything. Others are kind of shy and just prefer to keep to themselves. So, how do we figure out which metals are the social ones and which are the shy ones? Well, scientists don't just guess, they run tests. They carefully watch what happens when they mix different metals with everyday things like oxygen, water, and even dilute acids. And all of that careful observation gets organized into one super useful tool. It's called the reactivity series. Honestly, the best way to think of it is like a power ranking for metals, from the strongest down to the weakest. And this is it. This series is going to be your cheat sheet for the exam. It lists metals from the top to the bottom. Up at the top, you've got the really reactive ones, like potassium. And as you go down the list, they get less and less reactive, all the way down to gold at the very bottom. Knowing the order of the common metals here is absolutely key. But remember, this list isn't just random. The position of every single metal on here is decided by actual evidence from those lab experiments. Let's take a look at what that evidence looks like. So check out what happens when you put them in water. If you drop in some potassium, whoa, you get a really big energetic reaction. But calcium, it's much calmer, just a slow fizzing. And then you have copper, which does, well, nothing at all, not even in hot steam. See? You can already start to see the ranking taking shape. And the pattern just keeps going when you use dilute acid. Potassium it's violent. Magnesium fizzes like crazy, but it's a bit more manageable. And gold, you could leave it in a vat of acid forever and nothing would happen. It's totally unreactive. So the rule here is actually pretty simple. The bigger the reaction, the bigger the fizz, the flame, whatever, the more reactive that metal is, and the higher up it goes on our series. It's all based on what we can actually see. Okay, you get the series now, so let's do something really cool with it. We're going to use it to predict the future. We're talking about displacement reactions, and this is where you can use the series to figure out what's going to happen before you even mix anything together. This right here is the #1 rule you have got to remember. A more reactive metal can literally push out or displace a less reactive metal from its compound. Think of it like a stronger player swapping themselves into the game and telling the weaker player to go sit on the bench. Let's see it happen. Here's the classic experiment. We're starting with this bright blue liquid, which is copper sulfate solution, and we're about to add a regular old iron nail. And look, just a little while later, two things have changed. That nail is now covered in a brownish coating, and the blue color of the solution is starting to fade. Those are our clues. A chemical reaction has definitely taken place. But what actually happened? The answer, of course, is in our reactivity series. Go on, find iron and copper on the list. You see it? Iron is higher up. That means iron is the more reactive metal. It's the stronger one. So it has the power to push that weaker copper out of its solution. So what we're looking at is a swap. The iron from the nail has gone into the solution, and in the process, it's kicked the copper out of the solution. And those homeless copper atoms are what form that brown layer all over the nail. But wait, what if we tried to do it the other way around? What if we put a copper nail into an iron solution? Nothing. Absolutely nothing would happen. Why? Because copper is less reactive than iron, so it just isn't strong enough to make that swap. This rule only works one way. Okay, you know the rules now. It's time to put what you've learned into practice. I've got an exam-style question for you. Ready to give it a shot? So here's the question. If you put a piece of zinc metal into a solution of copper sulfate,
Will a displacement reaction happen? Yes or no? But before you answer, think for a second. What is the very first thing you need to do to figure this out?
That's right. The first step is always to go look at your reactivity series. Don't ever try to guess. The answer is sitting right there on that list. Using this tool is how you get the marks. All right, let's use this series together. First, scan down the list and find zinc. Got it? Okay, now find copper. What do you notice? Zinc is higher up on the list than copper is. And that one simple fact tells us everything we need to know. So the answer is a big, confident yes. A reaction will definitely happen. And the reason? It's because zinc is more reactive than copper, which means it's strong enough to kick the copper out of the solution. It's as simple as that. So let's finish with this little thought. We make our most expensive and precious jewelry out of metals like gold and platinum, the ones at the very bottom of the reactivity series. So why do you think that is? Well, it's because they are so unreactive, they won't tarnish or react with the air or water or your skin. They stay perfect and shiny pretty much forever.